Welcome to part 3 of the video series where we learn how to make a three-dimensional circular hose in Python. Now that we have the circular path and we also know what a Jacobian is, what we're going to do is we're going to use the Jacobian in order to find the normal as well as the tangent vector of the curve. In order to do that, we're going to be using what's called the Frenet-Serret formulas. So let's go ahead and take a look at what it is. Okay, so essentially what the Frenet-Seret formula tells us is that the tangent vector is the derivative of the curve's function with respect to its arc length, and the unit normal vector is the derivative of the tangent unit vector with respect to the arc length. So, in terms of the tangent formula, what we can write this as is, using chain rule, we can write this as the derivative of the curve function with respect to time times dt over ds. We've already learned that this particular expression is just the Jacobian of the curve function. So we can write this as the form, the Jacobian of the function as f divided by the derivative of arc length with respect to time. Now, let's take a look at what we can do with a normal vector. So, let's say we've got our normal vector as this. Now, again, we can apply the chain rule, so we can say this times ds over dt. Again, we can write this as the derivative of tangent vector with respect to time divided by the derivative of arc length with respect to time. Now, another thing is that say we have this part of the curve and it's got its origin, the arc has the origin, and this is at time t, and this is at time t plus dt. So this would be the radius at t, and this would be the radius at t plus dt. Now, what we know is that if the change in time is very small, or it approaches 0, then the magnitude of the derivative of the arc length with respect to time is approximately equal to the magnitude of the derivative of the function itself with respect to time. Now, the reason this is important is because the arc length is actually a scalar quantity, so it means it doesn't have a direction. So we can write these functions simply as the magnitude of the derivative of the arc length. And this, in turn, can be substituted by this value. So we can simply substitute the s with an f. Same thing goes here. You just write it as this. So we'll go ahead and calculate the tangent and the normal vectors in Python. And the main reason we're doing this is that we'll be able to find the binomial vector using the tangent and the normal vectors, since it's just going to be a cross product of those two vectors. So let's go ahead and do this in Python. So now I'm going to define our whole function as for the Frenet-Seret, so I'll just call it Frenet-Seret. And the first thing we want to do is get our dfdt, and we've already established that this is simply going to be the Jacobian of our curve function. So there's that. Now we want to calculate ds dt, so I'm going to define that as a function, and this takes the t as input, and it will return. We've already established that ds dt is simply the magnitude of our df/dt. So an easy way to do this in Python using JAX is that we use jax dot linear algebra dot normalize, and we'll feed our function df/dt to it at t. So that gives us ds/dt. After this, we want to find our tangent. So I'll describe that as a function as well. And we'll take t as an input, and here it will return. We've already established that our tangent function is simply our Jacobian with respect to divided by the magnitude, or ds/dt. So we're just going to write that as df/dt over ds/dt. After that, I want to calculate what dt ds is going to be. So, which is basically our normal. Actually, instead of dt ds, it should be dt dt actually. So this is also just going to be the Jacobian of our tangent function. So we have that, and finally, we're also going to find our normal vector. Let's define that as a function. Takes t as input, and it will return so our normal vector is simply going to be our tangent dt dt over df/dt. So that would be dt dt divided by our magnitude of that would just be the ds/dt. Now another thing here is that Frenet-Serret formula doesn't actually state this. What it actually says is it's true for the unit vectors. So what we'll have to do to change this is that we'll have to write this as the normal vector divided by the magnitude. So again, what we'll do now is instead of returning this, I'm just going to copy that and call it n. That will equal to this, and what we want to return is simply n divided by the magnitude of n, which can be calculated as jax.ln_out. That's actually jnp. I think we made a mistake here as well. jnp dot linear algebra dot normalize Rn. And we want this whole function to return the tangent and finally our normal. So there's that. Another interesting thing is that we can also find what our curvature is going to be. That can simply be calculated by finding the reciprocal of our normal vector's magnitude. So basically what we need to do is 1 over jnp dot linear algebra dot normalize. So we'll take our curve and we'll try to calculate our curvature at 0.0. So calculate that. So that's basically 0.33.